Benefits and disadvantages of natural light and solar heat gain. Welcome to Building Knowledge 101. Join us as we discuss the fundamentals of natural daylight, including the advantages and potential challenges it presents.
When we look at benefits, there are proven studies that show reduced operating cost in buildings, reduced turnover, absentee rates, greater engagement, greater involvement in the work area from increasing natural lighting and views. Now, there is a negative side of sunlight, and that is glare and solar heat gain. So I want to move and talk a little bit about that also. So glare is like you see in this picture, light reflecting off of surfaces on the interior, and solar heat gain is heat that's being brought in by daylight. So to begin that conversation, let's talk a little bit about what daylight is. Daylight is made of waves, and the waves are measured in nanometers. We're looking at the length between the peak of each of the waves. So what the human eye is able to see is what we call visible light. And visible light is waves that fall between 400 nanometers and 700 nanometers. Above that is what's considered infrared, and below that is what we call ultraviolet. So the human eye can see this spectrum from 400 nanometers to 700 nanometers. Now, what's fascinating about that is what a rainbow is. When you see a rainbow, what you're looking at is natural light, daylight. When the light hits moisture particles suspended in the air, it causes the light to bounce back and bend, and that bending causes the different wavelengths to separate. So when you see a rainbow, what you're seeing is daylight passing into a drop of moisture in the atmosphere, and it starts to bend or refract, what we call refracting. And the light bounces off the back of that moisture drop back almost the direction that it came, and it begins to bend even further. And what's fascinating about that is each wavelength has a different length. So each wavelength bends at a slightly different arch. Violet has the shortest wavelength, so it bends in an arc of 40 degrees. Red has the longest wavelength, so it bends at an arc of 42 degrees. All the other colors fall between that 40 and 42. So they're each bending at a different arc, and that causes them all to separate because they're bending separate from each other, so you can see them. So again, looking at a rainbow, you are now able to see all the different wavelengths within that. Well, I say you can see them because what we can see again is this visible light between 400 and 700 nanometers. Below that, shorter wavelengths are what are called ultraviolet lights. These are below 400. Now, the human eye can't see them, but that wavelength is out there. Ultraviolet light is what causes sunburn, skin cancers. It causes colors to fade, fabrics to start to break down. And if you've ever seen dashboards on cars that are starting to crack, that's because of ultraviolet light. Now, above 700 is infrared. Again, the human eye can't see that, but we have a lot of equipment and technology that can see infrared. Security cameras typically work with infrared. Night vision is looking at infrared. So using a camera, security camera that sees infrared, it can be totally dark outside. We can't see, but a camera using infrared can see perfectly clear looking through that spectrum. So those are all the waves that make up daylight. Now I mentioned there's a negative, and that's glare. There's also solar heat gain. So with daylight, when it enters a building, it also brings heat with it. When we look at the breakdown between those different categories of light, solar heat gain it's coming through in each of these categories, but ultraviolet consists of about less than 5% of the heat in daylight. Visible light contains 43% of the heat, and infrared light contains 52% of the heat in daylight. So your first strategy by trying to bring in more daylight into a building is looking at how you can cut down on this heat coming through the building also. So that's where glass manufacturers have done a great job of introducing low E coatings that are available on their products. Low E is a measure of emissivity, and emissivity is a measure of a material's ability to reflect or radiate heat inward. So a low E product does not have a good ability to radiate heat. It's reducing the ability of the material to radiate heat. So if you look at the illustration here, low E coatings on glass are bouncing the heat from ultraviolet back to the exterior. They're allowing visible light to pass through to the inside, but they're bouncing heat from ultraviolet back out to the exterior, which is what we want. We want daylight to come through, and we want to minimize the heat coming in with it. That is all we have time for in this video. If you'd like to watch more of our 101 video series, subscribe to our YouTube channel, Kawneer Company, Inc.